Say, Pete, what are you trying to prove with those jumper wires?
I'm checking out the wipers on this car, Ray. I want to find out whether the problem is in the linkage, circuit connections, wiper switch, or the motor before I start taking things apart.
Hey, that reminds me. When are you and Tech going to fill me in on your windshield wiper troubleshooting secrets?
Pete doesn't have any secrets, Ray. But he does know all about windshield wiper motors and understands how they work. With that kind of know-how, anyone can do a good job of diagnosing windshield wiper problems.
I'm sure you're going to bug me until I tell you all I know about wiper motors, so let's get on with it right now. Maybe Tech will stick around and lend me a hand.
I wouldn't think of missing this session, Pete.
3 different wiper motors are used on our 1970 models. These two are both 2-speed motors. From the outside, they look like twins, but they're quite different. The one on the left is a reversing motor. The other one is non-reversing. The third motor can be either a 3-speed motor or a variable speed motor, depending on the type of wiper switch used to control the speed. But let's take an inside look at each of these 3 motors so you'll understand exactly how they work and how the external circuits control speed and park. This 2-speed, non-reversing, permanent magnet type motor is probably the easiest to understand, so I'll start with it.
What do you mean by permanent magnet type?
In a permanent magnet motor, the field poles are permanent magnets. There are no field windings. This motor has a wound armature and 3 brushes. Next, I'll explain how each brush is connected for each wiper switch position. For low-speed operation, the brush at the top of the picture is the positive or feed brush. The brush on the opposite side of the commutator is the ground brush. As a matter of fact, this brush is permanently connected to ground in this non-reversing motor. For high-speed operation, the third or remaining brush becomes the plus or feed brush. Incidentally, this brush is 60 degrees away from the low-speed brush, and of course the lower brush is grounded. Any questions so far?
As a matter of fact, yes. Where does this resistor come in? Does it have something to do with speed control?
That's not its primary function, Ray. That resistor is connected into the circuit to the low-speed brush to limit low-speed torque.
Oh, now I am confused. There must be something I don't understand about electric motors.
I guess I better explain a couple of facts about direct current motors, Ray. The slower a DC motor turns, the more current it draws and the more torque it develops. That resistor in the low-speed circuit reduces torque so that the motor won't chew up the drive gears when the blades freeze to the windshield. Now, another fact about motors. In a direct current motor, the stronger the magnetic field or the more turns in the armature windings, the slower the motor speed. I know it sounds backwards, but that's the way it is, Ray.
Well, I'll take your word for it if one of you will just explain how that principle applies to this motor.
When the feed is through the high-speed brush, fewer armature windings are used, and the motor speed is high. When the armature feed is through the low-speed brush, more armature windings are being used, so speed is low. And that brings us to the park circuit.
When the wiper switch is turned off, the low-speed brush is fed through a different external circuit. This circuit goes through a parking switch built into the motor. The motor continues to run as long as the parking switch is closed. When the armature rotates to the point where the wiper blades are in their park position, the parking switch is automatically opened by a cam mechanism in the output gear. This cuts off all power to the armature. In addition to cutting off the feed circuit, the parking switch connects the low-speed brush to ground. So there are 2 ground brushes and no positive brush. This has the effect of connecting the low-speed and ground brush together to make a closed-loop circuit. As a result, the motor becomes a generator. Since there is no mechanical power applied to turn the armature, it stops right now, and the wiper blades park where they're supposed to instead of coasting.
I never realized there was that much to a wiper motor and circuit. But tell me, what's the linkage setup on cars having this non-reversing motor?
There are 2 links and 2 pivots, Ray. The drive arrangement is pretty much typical of most wiper systems. The outer end of the rotating drive crank is connected through a drive link to the wiper pivot on the left side of the car. A connecting link couples the left pivot to the right pivot. Any questions?
No, that's clear enough. But, well, maybe you can tell me, how is this other two-speed motor different from the one we've been talking about?
The two-speed non-reversing motor has 2 brass and 2 gray metallic terminals. The two-speed reversing motor has 1 brass and 3 gray metallic terminals.
2 brass terminals? Sounds like a big deal.
That's just the outward identifying difference, Ray. The circuitry and what's inside is another story.
The main differences are in the parking switch circuitry and the brushes. All 3 brushes are insulated. There is no permanent ground brush. Instead, the lower brush is grounded through the wiper switch for both low and high speed.
That's worth remembering, and here's why. A two-speed reversing motor won't run if the wiper switch isn't grounded. A two-speed non-reversing motor won't run unless the ground at the motor is good. Ray will tell you how ground circuits affect park operation a bit later. Now back to an inside look at this reversing motor.
For low-speed operation, the positive feed connection is through the torque-reducing resistor to the low-speed brush, and, of course, the ground brush circuit from the wiper switch. Except for the external circuitry, this is the same as for a non-reversing motor. For high-speed operation, the wiper switch feeds the high-speed brush, and the ground brush gets its ground from the wiper switch. The big difference in operation comes when we get to the park circuit. When the wipers are turned off, the wiper switch reverses the polarity of the brushes used for low-speed operation. The upper brush becomes the ground brush, and the lower brush becomes the positive feed brush. This reverses the direction of motor rotation. But notice, the feed circuit now goes through the parking switch built into the motor. So the motor will continue to run in reverse only as long as the parking switch remains closed. When the parking switch is open at the completion of the wipe cycle, the positive feed is disconnected. And as you probably guessed, the parking switch connects the lower brush to ground. In other words, both the upper and the lower brushes are now grounded, completing the closed-loop armature circuit. This puts the brakes on armature rotation, just like the non-reversing motor.
I know that this motor is used on cars where the wipers park off the glass and disappear out of sight. How does the motor do that?
That depressed park feature isn't built into this motor, Ray. Instead, this cam mechanism on the end of the crank arm makes the wiper blades do their disappearing act. But let me show you why the wipers travel farther when they go into park. As long as the motor and crank arm are rotating in a counterclockwise direction, the cam is in this position. The throw or effective length of the crank is about 2 5/8 inches. When the wiper motor reverses, the cam rotates clockwise, and the effective length of the crank throw is increased to about 2 7/8 inches. Increasing the crank throw a 1/4 inch causes the outer end of the wiper blade to travel about 4 inches farther to the depressed park position.
I get the general idea, but I'll study this cam action a bit more on my own to see exactly how it works. So what's next on the program?
I may as well cover the articulated link wiper arm used on the left side of the windshield while I'm at it. When the wiper blade and arm are near the lower end of the wipe pattern, the wiper blade is almost parallel to the wiper arm. As the wiper arm moves upward, the lower end of the wiper blade pivots away from the wiper arm. At the extreme end of the wipe pattern, the lower end of the wiper blade has moved about 4 inches ahead of the wiper arm, so that it is almost parallel to the windshield A post. The advantage of the articulated link mechanism is more wiped area and better visibility through the windshield.
Oh, I can see that. Now, how about this 3-speed or variable speed motor?
This is a 3-speed motor when it's controlled by a step resistance switch. It becomes a variable speed motor when a switch having a rheostat is used to control speed. In either case, the motor itself is the same for both applications. 2 separate field windings are used in this motor, a series field and a shunt field. The 2 fields are wound and connected so that they always have the same polarity. As you can see, a wound armature is used, and there are only two brushes. One of these is the ground brush, so the polarity of the armature never changes. Next, let's talk about speed control.
Hold it, Pete. It's time to turn the record.
Remember, we said earlier that the weaker the field, the faster a direct current motor goes. That's the principle used to control speed in this motor. Circuit-wise, here's how it's done. Full voltage from the wiper switch is fed to the series field and then to the armature. The resistance unit in the wiper switch can reduce the voltage applied to the shunt field. This, of course, reduces the strength of the shunt field, and the combined field strength is weakened.
And reducing the total field strength increases motor speed, right?
Correct, Ray. And it doesn't make any difference whether the wiper switch uses step-type resistors to reduce shunt field strength or a rheostat to give variable speed control. The end result is the same.
How about park?
When the wipers are turned off, the polarity of the armature stays the same, but the polarity of the field circuits is reversed by the wiper switch. This causes the motor to reverse and run in the opposite direction. But see what happened to the feed circuit. All the current flow is now through the parking switch built into the motor. Actually, the armature is now fed directly from the parking switch, and the two fields are connected in series with each other. After the motor reverses, it always completes one full wipe pattern before it goes into the final phase of the park cycle. This is referred to as the anti-streak feature, because the blade can't reverse halfway through a wipe cycle and leave a streak when it moves to its depressed park position.
Say, tell me, how does the depressed park feature work on this motor?
The extra crank throw is built right into the motor assembly instead of being part of the crank arm. Now notice, when the motor is turning counterclockwise, the crank arm is in this position. The center of rotation is here, not around the eccentric shaft, which provides the means of attaching the crank to the motor. Now watch. When the motor reverses, the wiper completes the wipe cycle. Then when the blades reach the end of the wipe pattern, the eccentric drive shaft and the crank arm rotate a half revolution. This over-travel action moves the blades off the glass and into the depressed park position.
What turns the motor off?
The motor runs until it reaches the lower end of the wipe pattern. At this point, a cam opens the park switch. This cuts off the current to both the armature and the fields, and the motor stops in the depressed park position.
Now that I've had my wiper motor and linkage lesson, are you going to tell me how you go about troubleshooting wiper problems?
Diagnosis is mostly a matter of understanding how the motors work and then applying a little logic and common sense. But I'll tell you how I go about it. First off, I want to uncover all of the clues I can before I take anything apart. It isn't easy to get at the drive linkage, particularly on compacts and intermediates. And replacing or getting to the wiper switch terminals isn't exactly easy either. I try to narrow the trouble down to the switch, the external circuit connections and wiring, the motor, or a bind in the linkage. It saves a lot of time and embarrassment if you make the quick and easy checks first. For instance, before you do anything else, turn the ignition key to the accessory position. Then try each wiper switch position to see what kind of wiper problem you're dealing with. Let's suppose the wipers don't work at all. In that case, watch the ammeter as you try each switch position. If there is no indication of discharge or ammeter deflection in any switch position, you probably have an open feed circuit. I'd be mighty suspicious of an open circuit breaker in the wiper switch. Of course, if the ammeter needle bangs over against the discharge stop peg and the circuit breaker pops open in a matter of seconds, chances are there's a dead short somewhere. This could be in the external wiring or possibly in the motor. On the other hand, suppose the ammeter shows higher than normal discharge, but not more than 10 or 15 amps, and it takes maybe 15 or 20 seconds to pop the circuit breaker. In that case, the wiper motor is probably stalled. Could be the motor or a binding linkage. Those quick ammeter clues help you decide what to do next. For instance, if there's no discharge, the obvious thing to check is the electrical connections. On two-speed motors, be sure and check at both the bulkhead and at the motor itself. And don't forget, even if the connector's tight, there could be a loose connection at one of the terminals inside the connector. If you have reason to suspect a bind in the linkage or pivots, reach into the car and flip the wiper switch on with one hand and give the wiper arm a gentle assist with the other. If a helping hand starts the wiper working, the problem's more apt to be mechanical than electrical. To check this out on a compact or intermediate, I reach up under the instrument panel, take off the crank arm nut and disconnect the crank without disturbing the rest of the linkage. If the motor works with the linkage disconnected, I know the bad news is in the linkage or the pivots. Since it's the easiest operation, I check for a binding pivot first, particularly if the car's a year or more old. Pivots are more apt to bind as the car gets older. Other linkage bushings tend to be tight when the car is new and get loose and perhaps noisy as the car gets older.
If you suspect motor trouble, do you have to remove it to check it?
Not if you understand how each type of motor works and have a copy of this month's reference book. How about it, Pete?
A set of jumpers is all you need to check out a motor without removing it from the car. To make it easier for you to see, I'll demonstrate how I use them to check out each of those three motors over there on the bench, starting with the two-speed non-reversing type. In practice, you can make the same checks on the car. To check low-speed operation, the red positive jumper is connected to the L terminal and a black negative jumper to the motor ground strap. When I connect the other end of the jumpers to the battery, the motor should run at low speed. Next, check high-speed operation by connecting the positive red jumper to the H terminal. Leave the black ground jumper connected to the motor ground strap. Reconnect the red lead to the battery. The motor should run at a higher speed.
You notice that Pete makes the connections at the motor terminals first and then connects the battery end. This reduces the likelihood of accidental shorts.
Right you are, Tech. To check park, use the short yellow jumper to connect the P2 terminal to the L terminal. With the positive red jumper connected to the P1 terminal, black ground jumper is still connected to the motor ground strap. The motor should run to park and then stop. For a low-speed check of the two-speed reversing motor, the black negative lead is connected to the P2 terminal and the red positive lead to the L terminal. To check high-speed operation, leave the black negative lead connected to the P2 terminal and move the red positive lead to the H terminal. To check out the park cycle, I connect one black ground lead to the L terminal, another ground lead to the motor ground strap, and the red positive lead to the P1 terminal. The motor should reverse and then stop in the park position. Actually, when checking a motor on the car, the jumper to the motor ground strap isn't needed if you're sure the motor ground is good.
But remember, if you don't have a good ground at the switch, a two-speed reversing motor won't run on high or low. If the motor ground is bad, it won't reverse and park.
Well, I hope I can remember all those connections.
You don't have to, Ray. You'll find all the dope in the reference book, plus some good tips on where to look for trouble if the motor passes all the jumper tests. I think we still have time for the three-speed motor tests.
Since the wiring harness is part of the three-speed motor assembly, you'll have to disconnect the motor leads from the bulkhead disconnect. Three-speed and variable speed applications use different bulkhead connectors, however, and the same wire color code is used for the motor leads in both applications. So the tests are the same regardless of the shape of the connector. To check high speed, connect a negative battery lead to the green wire terminal and a positive lead to the brown wire terminal. These connections feed the series field and armature but do not supply current to the shunt field, so motor speed is high. To check low speed, leave the jumpers connected to the green and brown wire terminals. Connect a second positive jumper to the red wire terminal. This feeds current to the shunt field, and the motor should slow down.
I get it. Adding the shunt field to the series field increases the total field strength, and this reduces motor speed, just like you said it would. How about testing park?
For the park test, the green wire and brown wire terminals are connected together by a short jumper. The positive jumper is connected to the blue wire terminal, and the negative jumper is connected to the red wire terminal. This should make the motor go through its parking act.
You just managed to beat the closing bell, Pete. Use what you learned about wiper motors today, Ray, and you too can be a windshield wiper troubleshooting expert. If you can't remember everything you've heard, use this month's reference book and your service manuals. Of course, the reference book covers everything we've talked about today. In addition, it has the latest dope on the new wiper arms used on full-size cars, plus some linkage and wiper switch service tips. Keep those books handy.